Okay, hello everyone. This is Doransin from University of Luxembourg. Today I'm going to talk about log-based slicing for sustainable test cases. This is a collaboration with Sama Messaudi, Annibale Panicella, Domenico Biancoli, and Lionel Briand. Let me start with the regression testing, which is arguably one of the most important testing activities in software testing. However, its cost effectiveness can be largely impaired by the cost of individual test cases. For example, let's consider this: 3 test cases, which takes at least 2 hours. In this case, even if a perfect test case prioritization technique is applied, no fault could be detected during the first few hours, simply because individual test cases take too much time. This is exactly the case what we observed from our collaborative industrial research project. There were many complex system test cases, but they are often very expensive, like took more than 1 hour to execute a single test case. Why? They trigger and wait for physical components that takes a lot of time to complete. On the other hand, some of the test cases are poorly designed, like containing multiple scenarios combined into a single test case. This is mainly because the accumulation of technical debt over several years of software development. So we thought, what if we decompose complex system test cases into smaller and less expensive ones? Maybe we can decrease the execution time of the decomposed test cases. We can improve the cost effectiveness of the prioritization, and providing finer grained testing result can facilitate debugging activities like fault localization and even program comprehension. Then the question is, how can we do this? A simple idea is program slicing. We can just decompose a complex system test cases containing multiple test scenarios into separate ones, so that each of them has only one test scenario and its corresponding test assertions. Let's think this simplified example of system test case that has only 2 assertions, lines 4 and 7. And by applying the static slicing, for example, on those assertion lines, we can decompose this test case into 2 decomposed ones. But there is a limitation of static slicing. If we apply the static slicing on line 4, then we can have this kind of static slicing result, because line 4 has 2 variables that are defined by lines 2 and 3. However, if we try to execute this one, it actually does not work. It returns some kind of runtime error because there is the output.csv file, which must be written by line 1, which is not included in the slice test case. So this slice case is not executable due to the missing hidden dependency, the dependency due to the output.csv file in this case. How about applying other program slicing approaches like dynamic slicing, for example? Well, it requires to instrument the source code so that it's not applicable to a system that is whose source code is not available. And more importantly, it does not address the problem of hidden dependencies because they are not captured by the code coverage. There is this observation-based slicing, which is again different from the dynamic slicing, but which requires to run each test case multiple times, so that by running those system test cases in trial error fashion, we can try to decompose the system test cases. But if the system test execution by itself requires at least 1 or 2 hours, then you cannot apply this one, obviously, due to the efficiency reason. So again, this is not applicable. Our new idea is using the execution logs that can be obtained from the past regression testing sessions. And I also want to note that these logs contain very valuable information, runtime information about the system and the test. And we can extract the global resource access, for example, the files or network connections, and the action performed like read or write on files, open and close of the connections upon executing each test statement. For example, this example log is the one that we can collect by executing the simplified test case that I showed you before. As you can see, by executing line 1, output.csv file has written, and by executing line 2, output.csv file has been read, and so on and so on. That kind of information is included in the log. So our approach, decomposing system test cases, in short DS3, takes two input, the system test case to be decomposed, and the system test case execution logs to refine the slice internally. And then it finally returns the final slice test cases. Initially, we perform the static slicing on the original test case, and then the candidate test case slices are generated by this static manner. And on the other hand, we analyze the depth use analysis, depth use of the global resources from the logs, and that information is used to refine the static slices. And the refined slices will go through the minimization step, which tries to remove any redundancy between the slices. I will explain each of the steps in more detail with the examples in the following slides. So step 1, the backward static slicing is the initial step we have to perform. Of course, this is straightforward because the static slicing is kind of standard procedure. So we can just apply the static slicing on each of the assertion statements. In this case, the assertion statements line 4 and 7 can be the slicing criterion, basically. And we have these two slice test cases. On the other hand, we can extract the global resource uses from the logs. So specifically in the form of the triple of statement, global resource, and the depth use, either depth or use based on the keyword that is written on the log message. For example, in this example log, we can identify that line 1 defines the output.csv file, line 2 uses the output.csv file, and so on and so on. So based on that, we can actually infer lines 2 and 3 depends on, or which can be simplified as this arrow, line number 1. After that, we do the log-based slice refinement by using the decomposed test cases and the missing hidden dependency information that is extracted from the global resource uses and depth. By analyzing this, we can actually add this missing dependency, missing statement, which is line 1 in both of the cases. So we can actually add them. And then we do the minimization check. This is actually from the observation that if all non-assertion statements of a slice are also in another slice, then we found that both slides share the same test scenario and therefore they should be merged. In this case, this is not the case because none of them is a subset of the other, so we do not need to merge them. So they are the final slices, meaning those two are the final decomposed test cases from the simplified example of the original system test case. Now I'm going to talk about the evaluation. So we basically aim to evaluate the following aspect of DS3, the three aspects. First, slicing effectiveness. Second, execution time of the slice test cases. And third, test effectiveness of the slice test cases. As an evaluation subject, we use two different data sets. One is from the proprietary data set, and the second one is JSBC, which is the open source one. Yeah. And for prop data set, we have 30 different test cases. For JSPC, we have originally 81, but since 5 of them are either flocky or non-deterministic, we removed them, so we have used only 76. If I recap, the research questions can be formalized as follows. RQ1 basically investigates how effective DS3 is in slicing system test cases into sliced ones that successfully compile and have no runtime errors. then this is compared to the slicing result of using only the static slicing without any refinement based on the logs. RQ2 assesses the running time of generated test slices compared to the corresponding original ones. And RQ3 analyzes the code coverage and the fault detection capability of the generated test slices compared to, again, the non-sliced original test cases. This table shows the RQ1 results, which is slicing effectiveness. If we focus on this red part, which is the total number of slices, you can see that for prop dataset, DS3 generates 137 slices, while a static slicer only can did generate 166, which is larger than DS3, simply because DS3 has this slice minimization step in the end. You have to focus more on the failing part because DS3 has no failure, meaning that none of the decomposed test cases cause any unexpected runtime error. However, if we use only the static slicing, most of the case, the decomposed test cases does not work well. So we can see that the static slicer has significantly lower slicing effectiveness than DS3, and leveraging the global resource uses and deaths reported in the logs, DS3 is able to generate well-formed slices in all cases. To research question 2, we compared the execution time of the generated test slices with the execution time of the original test cases. We ran each test 10 times to account for the uncertainty in the test case execution time measurement. As you can see from the table, on average, the execution time of a slice test case is much less than that of the original test case, which is as expected. There are some test cases where the total execution time of all slices of a system test case is actually greater than that of the original test case. And this makes sense because there are some cases where the same fixture is shared by the multiple slices. So yeah, reasonable. However, there are some very interesting cases. Even the total execution time of all slice test cases is much less than that of the original test case, like the TC30. This is mainly because the original test case has expensive statements that actually does not have any dependency on the others. So those statements are kind of useless statements and can be removed from the original test cases. But this was not indeed known before we applied this kind of decomposement. After applying DS3, the engineers indeed understood that, okay, there were some useless statements in the original test cases, which must be removed to further improve the cost effectiveness of future regression testing, which is very interesting. For test effectiveness, we measured coverage in terms of branch, function, and mutants. So basically, we count how many branches are covered, how many functions are covered, how many mutants are killed. As you can see, the original test case and the slice one has not much difference, meaning that slice test cases are as effective as their original test cases in terms of coverage and fault detection. Of course, there is a minor difference, and this is again because of some original test cases include useless statements that actually does not have any dependency to the other statements. In conclusion, I present VF3, which can automatically slice expensive test cases into far less expensive and smaller test cases. And then those slice test cases rarely decrease the effectiveness compared to the original one. And the slice one can be further utilized by, for example, different types of regression testing, like test case prioritization, test tree selection, to further increase the cost effectiveness. Thanks for watching this video. And again, this is Donghwan Shin from University of Luxembourg. You can find my email address here. Please feel free to contact me if you have any question or ideas to discuss further. Thanks a lot.